Okay, so shall I start? Yeah. Okay, so all right. Okay, so thanks very much for the invitation to speak here. I think I met Alex maybe a quarter century ago, 25 years ago. I was a graduate student at Yale, and Alex was visiting maybe for 2 months, maybe every year. And at the time, Yale was a bit of a sleepy place. But when Alex came for 2 months, everything started to. There was a lot of activity here and there, and great talks, and he would lecture an entire course in 2 months with many open problems. So many of my fellow graduate students got their thesis problem from Alex. And I remember also that there was maybe in 2002, maybe 24 years ago, there was a Midrasha also here that Alex helped organize, and he told the graduate students at Yale to come, and I thought maybe it's a good idea to come. So there was a great program with many speakers from all over the world. So I came here, and suddenly everybody had cancelled. So it was exactly the same situation as today. But in the end, so I thought, okay, maybe I came for nothing. Everybody's gone. But in the end, it was a fantastic event. I even gave a talk, maybe one of my first talk I gave as a graduate student, and I met many friends, and it was a great thing. So so happy birthday, Alex. I wish you many years of many more decades of exciting mathematics, and thank you for everything you've done to mathematics and to the community as well. So I'm going to tell you today about a joint work with Oren Becker, who is a student of Alex, and it's going to be about expanders, so expanders for finite simple groups. So this is a topic that has been started by Alex. And maybe in the early 90s. So I'll state the definition of an expander, even though everybody knows here what it is. So, but just to fix notation. So for me, an expander Kelly graph. So you have a group, finite group G, and you have a generating set S. So that's a finite group. This is a generating set. And you're going to say that it's an epsilon expander if the following holds. So if you have the following inequality. So there are many ways to define the notion of being an expander, but that's maybe the easiest way. So B here is an arbitrary subset of G with size at most G over 2. Okay. So and so this is for a given Kelly graph, or given G and given S. But of course, when you see this, you want to ask what is epsilon in terms of S, in terms of G. And so I'm going to define to say that G is epsilon expanding if GS is an epsilon expander for all S. So for all generating sets.
Now, this SB includes also B somehow, or
S.
SB.
So yeah, sorry. So S times B.
All the products of an analytic format?
All the products, but it does not include the set AB.
So it does, because I want to say that one contains S.
So you always.
Yeah, I'm going to say one contains S. Yeah. If one does not contain S, otherwise it's not true. So if you take, for example, S equals two elements, A and B, then it's not true with this formulation. Okay. So yeah. So that's the definition. And there's a beautiful paper by Alex and Benji from 92, which asks the following question. So it does many things, but it's one of the questions it asks is whether being an expander is a group property. So in other words, can you find groups that, or families of groups that are expanders with respect to one set of generators and maybe not expanders with respect to other set of generators? So, or can you find groups for which, or families of groups for which they are, it's epsilon expanding for some fixed epsilon. So does there exist a infinite family of finite groups that are epsilon expanding for some epsilon. Okay, for some fixed epsilon. So they ask this question, and they also say that maybe a candidate would be the family SL2P, where P belongs to the family of all primes. Okay, so that's the question, and so they also ask the converse question, which is can you find infinite family of groups which for some generating sets, choice of generating set is an expander, for some other is not, and this they didn't solve it in this paper, but then in a later paper by Alon, Alex, and by Noga Alon, Alex and Avi Wilgerson, where they talked about zigzag products. I think Avi will talk about this later this week. They show that SL2P acting on F2 to the P plus 1 exhibits generating sets of bounded size for which it's both. It can be both expanders and non-expanders. So it's not a group property in general. Okay. Now we know by work of Kasabov that also the symmetric group is like that. So you can find generating sets that are expanders and those that are non-expanders. But I won't be talking about this. I will mostly be talking about finite simple groups. And in the case of SL2P, in 2010, together with Alex Gambert, we answered Alex and Benji's question positively, and we showed that yes, there exists such family. But we did not manage to prove that the entire family of SL2P is like that. But we managed to show that mostly for most primes it's true. So we proved that there exists a. So we proved that there exists a family P prime.
It's time to move to another market.
Thank you. If I can find one. Yeah, that's not so good.
The ones in the bucket.
In the bucket, yeah.
Some new. Yeah.
Some are new. No. Better, yeah. Not so
Sometimes
good.
ones
Take a while to.
It's okay.
Okay, that's okay. So yeah. So we proved that there exists a subfamily of primes, p prime, which has density 1 among the primes, and such that the family SL2p, p in p prime, is epsilon expanding. And so, and there is, and we show that there exists a uniform epsilon. Okay.
Density is just the intersection with any finite interval is tending to 1.
Yeah. So in fact, it shows the following. So we show that p prime intersected with 1x. Actually, the complement. Show that the complement p minus p prime intersected with an x is at most x to the delta for every delta in 0, 1. So that's so the complement is very small, right? Because I remind you that by the prime number theorem, this is roughly x over log x. Okay, so the first main result of today is a generalization of this work to arbitrary rank. Yeah. So first of all, So the conjecture. So I wrote this down in the paper, in my ICM paper. That the conjecture is that it should be hope that the family of all finite simple groups of rank at most r is epsilon of r expanding. Okay, so this is still an open problem. Okay, but our first theorem, theorem 1, so it's almost all prime theorem. And it says this, so it says, what is it here? So for every delta, there exists epsilon, which depends on delta r, such that g of p is epsilon expanding. If the rank of g is at most r, and p is not in a family p delta, which has this property here. So p delta is like this. Okay. So so there is epsilon, there is a family p delta, which may be empty, we hope, but with this property.
So what's the difference between theorem 1 and the 2010 theorem?
This is for SL2 only.
Oh, only
Okay. Yeah, so that's theorem 2. Okay, so this is theorem 1. Right. So here G is simple, but remark this also holds for G semi-simple and even for G perfect. So there is a way to go from semi-simple to perfect, which uses some work of Lindenstrauss and Varjour, and some more recent work of Golsefidi and Srinivas. where they have a method that if you have a certain spectral gap for a semi-simple quotient, allows you to lift the spectral gap to a group that, like a perfect group, that has this semi-simple quotient as a quotient, and with kernel something nilpotent. So you can upgrade these results from semi-simple to perfect. Yeah, so by this I mean G, so G is G of P, and this is also G of P. And G is a fixed algebraic group over Q. So the counterexample here is not, this is not the FP points of a fixed algebraic group over P. Okay? Yeah, thanks. Okay, so that's theorem one. So how about prime powers? Okay, so it's going to be theorem two. Right. Okay, so prime powers. So Q is P to the n. So for prime powers, we have already a theorem which I contributed to with Ben Green, Bob Guralnik, and Terry Tao in 2015. We showed that for almost all generators, you have expansion. So we showed that we show that there exists epsilon and there exists delta, which depend only on R, such that for every G, for all but G of Q to the power 2 minus delta pairs AB in G of Q, the Keddy graph G of Q with respect to AB is expanding. So is an epsilon expander. Okay, so this is a power. It shows a power saving. So it shows that if you pick at random a pair AB and in G of Q, then okay, it was known before that if you pick at random a pair, it's going to generate the group. But we showed here that not only is going to generate the group, but it's going to be an expander. And the set of exceptions has a power saving. The number of exceptions is small, so G of Q 2 minus delta. Okay. All right. So the proof of this, and also the proof of the first theorem, uses the Bourgain-Gabaud method. I will mention in a minute. But before I get there, I want to state theorem 2. So theorem 2 is an improvement of this, so it's a kind of a dimension 0 theorem. It says that for every delta, there exists an epsilon, such that so let me just.
What is G of Q? G of Q is G of the finite group with Q element?
That's right.
Finite group with Q
So G of Q is you have your finite simple group. It's G of F of Q. Okay. So I'm not going to go into the details of the definition of finite simple group of Lie type, but you could take SL2 of FQ or SLN of FQ, or you could take a Chevalier group and take the FQ points, or you could take a Steinberg group, so you take G would be defined over FP, maybe a twisted form, or it can even be the Suzuki and Rie groups, which are even more twisted forms. but which are the full list, yes, of finite simple groups. This is not true for alternating groups, so there's R here, okay? I don't know, actually I don't know if it's not true for alternating groups, but this is not what we show, okay? But we fix the rank here, okay? So R is the rank. The rank is like for SL2, the rank is 1. The rank is related to the dimension. It's basically the square root of the dimension of G, roughly. So, right. So this is, let me just, I'll finish stating this. So for every delta, there is an epsilon, such that for all but Q to the delta conjugacy classes of generating pairs AB, we have an expander. So G is epsilon expanding. Okay. So yeah, you have to look at conjugacy classes, because of course if you have a generating pair which is a counterexample to the conjecture, so with a very bad spectral gap, then of course every conjugate of this pair will also give you the same spectral gap. So won't work, okay? And so if you have a bad pair, then maybe the full conjugacy class will have size at least Q. So that's why we have to just count conjugacy classes instead of counting pairs. Okay. So this shows that the set of exceptions to this conjecture is very small. So it's kind of dimension 0, because you can get at most Q to the delta of such.
Can you say again what is the conjugacy class?
Yeah, so it's the diagonal conjugacy class. So you act diagonally like this. Okay. Okay. Okay, and so the problem is that so I will explain how these exceptions arise in the proof. Actually, there was a time before the talk when I thought this clock was right, but and I realized it's not. Okay, so now I can state theorem 3. Yeah.
So in the expander you meant to write the conjugacy class?
Sorry?
So if AB doesn't give an expander, then also if you conjugate it with some elements, you're not getting the expander.
Yeah.
So what is the relation of the conjugacy class to the theorem?
So I'm saying that I want to understand for which pair AB this is an epsilon expander. Okay, and I hope that maybe it's true for all pairs. There is a uniform epsilon for all pairs. I'm saying maybe I don't know how to prove this, but I can prove this for most pairs. So for most conjugacy classes. So the pairs, you can put them into conjugacy classes. For each conjugacy class, if you have some epsilon, for one pair, you have the same epsilon for any other pair of the same conjugacy class. So you can think of good conjugacy classes and bad conjugacy classes. And this says that there are only very few bad conjugacy classes. So another result is super strong approximation. So again, I'll put a caveat here, I mean a qualifier, almost all. So what does this mean? So what is super strong approximation? So super strong approximation, you have G, is semi-simple or even perfect, it's fine. Perfect algebraic group. And you define it over a global field, so in the typical case, you look at G of Z, G of Z, and you reduce modulo primes. And so strong approximation is a theorem that tells you that if you start with a Zariski dense subgroup of G of Z, and you reduce modulo a large prime, then eventually the map from the Zariski dense group to G of Fp will be surjective. Okay, so this is true if G is simply connected, and it's almost true if it's not simply connected. Okay, so that's strong approximation. Super strong approximation is a statement that not only it's generating G of Fp, but it's an expander. The image of the Cayley graph, the image of the Zariski dense group will give you generators that make the quotient to an expander. And so super strong approximation was proven by Gorsefidi and Variou in characteristic 0. And it's still an open problem to generalize this to characteristic P. So what this says is it's not a proof, but it's I'll tell you what we get. We get that suppose sigma belongs to G of Fp of t is a finite set, and suppose that the group it generates, called gamma, is Zariski dense. Okay. Well then, for every delta, you can find epsilon, such that for every q is a prime power of p. When you can specialize. Look at the specialization that sends t to alpha. Okay, and alpha is an element of fq. And so that's like a reduction modulo a prime ideal in fpt. And this gives you a group pi alpha of gamma, which typically is a finite simple group when G is simple, but otherwise will be G of a finite field. And here you have a generating set of pi alpha of gamma, and we claim that this is an epsilon expander. So epsilon depends only on delta. And what is delta doing here? It says that it's an epsilon expander, maybe not for all values of alpha, but for all but q to the delta values.
Excuse me.
Alpha in fq.
I'm sorry, I can't see what's written in this little corner, just like it's
What?
like there's yeah.
So should I remove do this?
It's like a little bit lower and a little bit more.
Like this?
Yes. That's right.
Okay. Yeah. So I'll just rewrite this right there. Okay. I can move it. Ah, yeah, very good. Excellent. So, expander, yeah, so, okay. Thank you for suggestion. Okay. So this is what we're hoping for, is that this projection becomes an epsilon expander for all values of alpha. Okay. But this says that it's true, but for all but q to the delta values. Okay. So it's similar to saying that, you know, in characteristic 0 it would be like you reduce modulo prime, but not modulo all primes, but modulo most primes. So here it's similar. You reduce modulo most irreducible polynomials in FP bracket T. Okay.
Can I ask, in characteristic 0, there's also the issue of primes versus square free versus...
Yes, indeed. So I would say one thing about this, is that our paper is 20-page long. If you want to go from prime reduction to square free or arbitrary moduli, the length of papers typically increases by a factor of a significant factor. So so we're only dealing with factorization by prime ideals here. Okay? So if you have it by prime ideals, you have it. You also have it for maybe for products of so not only one value but two values of finite number of values. But if you want all square free, that's it's harder work. No, it doesn't. So I'm sorry, this is not yet on the archive, but Alex, you will get a preview before your birthday, I promise. Yeah, it's okay. So, fine. So now I want to say a couple of things about the proofs. So maybe, not so. Okay, should have thought. Okay.
Trying to move an unmovable black hole.
Yeah.
The audience maximum.
You mean like this?
Yeah.
Okay. So I'll stick to this for the moment. Okay. So the theorem 2 and theorem 3 are new for SL2. Okay. Already. Okay. So I'll describe some of the methods. So underlying here, there is the what's called the Breuillard method. And this is a method that was invented in Princeton in 2006 when Alex was leading a program at the Institute on expanders and representation theory. And in this seminal paper, Breuillard showed that they solved the Lubotzky 1, 2, 3 problem. Okay. And the 1, 2, 3 problem was about showing that SL2 FP with the generating set, with this generating set, when n equals 1, 2, or 3, does this form a family of expanders when the prime goes to infinity? Alex knew how to do it for n equals 1, for n equals 2, but not for n equals 3. Okay. And Breuillard proved it for n equals 3. In fact, they proved it for every n, and they proved actually that if you start with a Zariski-Den subgroup of SL2Z, then when you reduce modulo primes, you get an expanders, which is the super strong approximation case in characteristic 0 for SL2. So what this method requires is the following things. It requires three things. So it's actually a general method that allows you to get spectral gaps to prove the expander property from for an arbitrary K graph of a finite group. Okay? But it requires certain conditions on a K graph, so on the group. So it requires what's called quasi-randomness. This is a terminology due to Tim Gowers that wrote an influential paper called quasi-random groups. But what this really means is just that the dimension of irreducible representations, of complex irreducible representations of G cannot be too small and is bigger than G to the beta, where beta is some fixed number. Okay. So if G is a finite simple group, this is known to be the case, and in this case, beta is like the rank over the dimension. So it depends only on the rank of the group, okay, and not on the size of the field. So that's quasi-randomness. The second ingredient is classification.
By the way, I think it was Bernstein and Dunn that pointed out this quasi-randomness is useful in explaining.
Right. So, yes, there were precursors to this. Bernstein, Kashdan, Sarnak, Shui. There was, this idea would be useful for proving expanders. Was around. So, classification of approximate groups. So I'm not going to define approximate groups here, but I just want to say one way to formulate this is that what is needed is a so-called product theorem, and what this means is that the triple product of any subset in G needs to be larger than either the full size of G or the size of A to some positive, strictly bigger than 1 power. Okay. And this okay. In fact, the theory of approximate groups was mostly driven by applications to expanders, and so when Bougain-Gombo did this for SL2, this was proven then by Helfgott for SL2P, and then it was generalized by Pibel-Sabo and Grimenthal and myself to arbitrary finite simple groups of Lie type. So the epsilon note here depends only on the rank of L. Okay? And the third ingredient is a non-concentration on subgroups, is the non-concentration on subgroups. So I'm going to say what this means. Okay, so maybe I'll just go there. So this means that if you take a proper subgroup, so H in G, and you look at the probability when you take a large word of length L, the probability that W belongs to H, W is a word, non-reduced word of length L, so it's kind of a random word, that's a random word in A and B. And the probability that this belongs to H is small, and it's less than some G to the kappa. When L is larger than a small constant times log G. Okay. So this is called non-concentration on subgroups. The idea is that if you can prove, so this is a necessary condition for expansion. If you can prove expansion, you have an epsilon. This gives you, this expansion for K graphs is actually equivalent to fast mixing of the random walk on the K graph. So fast means logarithmic mixing. So you get mixed in logarithmic time. That's equivalent to being an expander. But of course, if you're mixed in logarithmic time, it means that when L is roughly log G, the probability that you belong to a subgroup H will be roughly the size of H divided by the size of G. And because you are in SL2P or in finite groups of Lie type, the subgroups are very small. There are no large subgroups. So typically H over G will be smaller than a small power of 1 over G. So this is a necessary condition, necessary for expansion. Okay. You might think that this is actually the most important thing, most important point to prove, right? And indeed it is, except that in some cases you have this for free. So for example, if you, in the 1, 2, 3 problem, then you have this more or less for free because if P is large prime and you look at the W of AB here will be a word in these two matrices. So the matrix entries will not be bigger than some exponential of L. Okay, so fixed exponential of L. So if L is larger than C log G, in fact the entire ball of radius L, of radius log G in SL2Z will be mapped into the quotient injectively. So you're going to get the random walk, the Cayley graph will look like the Cayley graph of SL2Z, or of this Zariski-Dense subgroup. Okay, so then showing this is just a matter of showing that you can lift everything to the characteristic 0 group to SL2Z. So in some cases, when A and B are given, for example, in that case, this is for free. But in most other cases, it's not for free because you have no clue how to bound this probability. So, and what's the punchline of the Bourgain-Gombrun method? Well, punchline is that if you have, so here, if you have 1 plus 2 plus 3, then this implies epsilon expansion, where epsilon is a function only of these parameters, so of kappa, c, beta, and epsilon 0. Okay? So for finite simple groups, this is for granted. This is Landazuri and Zeitz, or Frobenius in the case of SL2. This is also now established by work of Piva, Sabo, and myself and Green-Tao. So the question is really 3. Okay, so you have to prove something like this. Okay.
You mean in the context of like the theorem 3 that you mentioned? Like if you want to recover theorem 3 or also in the previous?
All 3. All 3 theorems.
Did you already showed us where the small set of prime, exceptional primes, enter the
No.
picture?
I will. Yeah.
H here, G here is the finite group or the...
Finite group. Okay, so this is true for an arbitrary finite group. This is true for an arbitrary group. So what is expanding here is G with respect to this generating set given by A and B. Okay. Yeah. Okay. All right. So where did this come from, and where does the restriction on primes come from? Okay. So maybe I'll erase this. Okay. All right. So the idea to tackle this probability is to so what is the probability that W of AB belongs to H? So how do you understand this? Okay. Well, 4 to the L words in A and B of length L. So let's call this set WL. Okay. So to understand this, you need to say, well, you need to say when, for which word W, does this belong to H? Okay. There may be many ways in which W of AB belongs to H. Okay. And the set of W's in WL such that WAB belongs to H, what kind of set is this? So this can be some set, E. It's a subset of WL. But a priori, you have lots of such sets. You have 2 to the 4 to the L subsets of WL. So, okay. So the idea to understand this is to, of course, view things algebraically, and to say this is, of course, an algebraic map. It's a word map. And this is an algebraic group, usually. It's a proper subgroup of G. G is an algebraic, is the FP points of an, or FQ points of an algebraic group. So the proper subgroups in finite simple groups, they are of 2 types. Either they are structural subgroups, namely they are the FQ points of a proper algebraic group, or they are subfield subgroups, namely they are G of FQ prime, where FQ prime is a proper subfield. Okay? So you need to understand both cases. So, but okay. But to begin with, I'd like to first look at the trivial case, where this is the trivial group. At least we need to understand this. Okay. In fact, for SL2, this is all you need to understand. So, for each subset E in WL, I want to consider the variety VE, which is the variety of all pairs, such that W of AB is equal to 1 for every W in E. Okay. So this is an algebraic variety. And I want to, so it's an algebraic subvariety of G cross G, but I want to view it in the set of conjugacy classes. So I will look at this. Inside G cross G, so G cross G double bar G means the conjugacy classes. The algebraic is actually the character variety of the free group of 2 generators with values in G. So this is the GIT quotient when you act by conjugation, diagonal conjugation. So this gives you a variety here. Okay? So the main point, one of the main points, is that although there are super exponentially many possible subsets of WL, there can be only, so the fact, there are at most exponentially many, so 2 to the O of L, possible geometrically reducible components of VEs. Okay. So a geometrically reducible component of VE, I call it C, I will call this an L type. Because
when you run over all the possible E's, you get only this many possible
varieties. Okay, not variety. So the set of V's may be very large, but the set of irreducible components will be at most exponential. Okay, So, yeah. Um, yeah. So this says that there are few L types. And the L type governs, if you belong to a given L type, it governs completely which words will vanish on AB. Okay. So I would say that C is thin if the probability that so E of C will be the set of words that vanish on C. Okay. And I would say that it's thin if E of C is less than 2 to the minus CL, so it's exponentially small. And otherwise, I will say it's fat.
What's the notation now? What of E of Q? The first, like,
This?
that's C.
Yeah, that's
These
it.
are all the L types, but the answer say that C is thin if, what's
If the probability, so it's a probability, so it's in WL, okay, W equals L. Okay, so E of C is a subset of words, and it's just the number, the size of E of C divided by the size of WL. So yeah.
And small c depends on...
And small c will depend only on G, okay, on the rank. Okay. And so the proposition here, this. Proposition is that if C is fat, then either the dimension of C is 0, or C is contained in the degenerate variety of G. So this is the set of pairs AB, which generate a subgroup which is not Zariski dense. So this is a degenerate variety. So if you look at pairs A and B, maybe they can commute, maybe they can have a common eigendirection, or they can. So they may not generate a Zariski dense group. So you can look at the set of pairs that do not generate a Zariski dense group, and it turns out this is an algebraic variety. Okay, so this is called the degenerate locus. So the claims that if C is fat, so you don't have this, then it has to be contained, it has to be degenerate, or it has to be of dimension 0. Okay. And this is where the problem comes. That I cannot rule out that there may be dimension 0.
Suddenly you move to G, which define the infinite field, because before that
No.
G over 5 was mean
Yeah.
that the group generally then is not Zariski dense. It's a finite group.
No. So G. So let's think of little g is G of FP or G of FQ, and here I look at G like the scheme G. Okay. So I work not over FP but over an extension with infinitely many transcendental extension of FP. So this defines a scheme, a well-defined scheme. So it means that the elements of C is an algebraic variety. It's a geometrically reducible component in, this big algebraically closed field over FP. And this says that either dim C equals 0, in which case C is just a point, or it satisfies these equations, which are the equations that define when it's not Zariski dense.
What's the relationship between this little c and the constant in this big O?
So the constant in the big O depends only on the rank,
Both of them.
but completely explicitly. This also depends only on the rank and comes from a theorem that I'm going to state.
But I should think of little c as being a very tiny constant.
Tiny constant,
So that's good enough for it.
yes. Okay. So C here will have dimension 0, but what's happening is that the degree of C, so C is a component of a VE, and VE is defined by equations which are word equations. Each word has length L, so typically they have degree L, and so you have a bunch of equations of degree L that we intersect together, and therefore the geometrically irreducible components that arise from this intersection, they, by Bezout's theorem, they have degree L, not L, but L to some power, depends on the dimension. But crucially, this power may not be 0, and the fact that this power may not be 0 is the issue. So that's the problem why you have to remove a small set of primes. It's the problem why you may not discard completely these finitely many these dim 0 components. So I call this dim 0 components. If dim C equals 0, I call C a scar. Because this corresponds to a pair which somehow, when I look at the words, all the words applied to this pair, there would there would be too many words that are equal to the identity. So for this pair, the associated K-graph of the group looks like it pretends to be. It generates G of Q, but it sort of pretends to generate a proper subgroup of G of Q. So it pretends to generate maybe G of Q prime, where Q prime is much smaller than Q. Okay, so it's a little. So this is, maybe in quantum chaos, people talk about scars when they have these periodic trajectories that somehow. Even though the system is chaotic, you still see these periodic trajectories that appear, even though the system is not periodic. So here it's a bit similar, completely purely semantic an analogy. That these pairs A, B maybe pretend to belong to a subgroup while actually they generate. My hope is that they don't exist at all. If they do, we may have a counterexample to the main conjecture. Yeah. 2 minutes. I finish. I just state the theorem that allows us to conclude. So the theorem, theorem 4. So this proposition here is a consequence of theorem 4. Theorem 4 is a kind of non-abelian Littlewood-Offord theorem. So Littlewood-Offord theorem. So it says this. So suppose you have x1, xn, some random variables with values in G of k, little k. So little k here is a local field. It doesn't matter which local field you take. And suppose that the probability that xi belongs to a coset of a proper algebraic subgroup is less than 1 minus beta. Then the probability that the random product belongs to a variety V is less than a constant that depends on v in explicit way times an exponential bound like this, and that's true for every v variety, an algebraic variety inside G. Okay, and the CG here is independent of the field, independent of the characteristic also. Okay. So I won't discuss the proof of this, but this is on the archive. The proof uses action on projective space and some Diophantine considerations, theory of heights, all that. So I'll stop here. Thank you.
Curious, Emmanuel, you described the proof when H, for example, is algebraic, there are non-algebraic, you can read of them by Larsen-Pink, or you need Ashbacher and then particular the classification?
No, only Larsen-Pink.
Only Larsen.
Only Larsen-Pink. Yeah.
What about SO3?
Good point, but one thing at a time.